National Electrical Code Section 250.24. A5 states that the grounding electrode conductor shall be connected to the equipment grounding conductor at the service disconnecting means or the overcurrent device or devices for feeders. This article specifies a single point of connection for the grounding electrode conductor, typically at the service disconnecting means or the first overcurrent protection device. Section 250.32 specifies that a grounding electrode conductor is required for grounded electrical systems. Grounding electrode conductors are used to connect the grounding electrode to the equipment grounding conductor, the grounded conductor, or both, at the service equipment or at the source of a separately derived system. Section 250.58. V prohibits the use of a neutral conductor as a grounding electrode conductor. This section reinforces the separation of the neutral conductor's function from that of a grounding electrode conductor, preventing it from being used as the sole path for grounding the electrical system. Now let's discuss the interpretation of these rules. According to Section 250.24. A5, the grounding electrode conductor must be connected to the equipment grounding conductor at the service disconnecting means or the overcurrent device for feeders. This implies that the neutral should only be grounded in one location, generally at the initial point of overcurrent protection. Meter bases aren't always considered a means of overcurrent protection, especially if they lack circuit breakers or fuses. Furthermore, Section 250.58. B restricts using a neutral conductor as a grounding electrode conductor. Connecting the neutral to the grounding electrode conductor at both the meter base and the main overcurrent protection could breach this rule. It is reasonable to advocate connecting the grounding electrode conductor to the equipment grounding conductor at the main overcurrent protection device, excluding the meter base. This aligns with National Electrical Code requirements and ensures proper electrical system grounding. Grounding is crucial for electrical safety. A grounding system provides a low impedance path for fault current, facilitating the operation of overcurrent protective devices like circuit breakers or fuses. Proper grounding minimizes the risk of electrical shock and equipment damage. When installing a grounding system, first identify the service disconnecting means. This is typically the main breaker or fuse box where the electrical service enters the building. Next, locate the grounding electrode. Common grounding electrodes include metal underground water pipes, concrete encased electrodes, ground rings, and ground rods. Then connect the grounding electrode conductor to the grounding electrode in the service disconnecting means. Ensure the conductor is sized appropriately according to National Electrical Code Table 250.66. Inspect all connections to ensure they are tight and free of corrosion. Use approved connectors and methods for making grounding connections. Verify the grounding system's effectiveness by performing an impedance test. This test measures the resistance of the grounding path to ensure it is low enough to facilitate proper operation of overcurrent protective devices. Avoiding common grounding mistakes is important. Do not ground the neutral in multiple locations. Grounding the neutral at multiple points can create ground loops and increase the risk of circulating currents in the grounding system. Do not use the neutral conductor as a grounding electrode conductor. The neutral conductor should be kept separate from the grounding electrode conductor to avoid potential hazards. Do not undersize the grounding electrode conductor. The grounding electrode conductor must be sized according to National Electrical Code Table 250.66 to ensure it can safely carry fault current. Do not neglect to inspect and maintain the grounding system. Grounding connections should be inspected periodically for corrosion or damage and repaired as necessary. Now let's look at the role of overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, protect electrical circuits from excessive current flow. These devices are designed to interrupt the circuit when the current exceeds a predetermined level, preventing damage to equipment and reducing the risk of fire. The National Electrical Code mandates that overcurrent protection be provided for all electrical circuits to ensure safety and prevent hazards. Proper overcurrent protection involves selecting the correct size and type of overcurrent device for the specific circuit. The overcurrent device should be rated to protect the circuit conductors and equipment from overloads and short circuits. Regular inspection and testing of overcurrent protection devices are essential to ensure they are functioning correctly and providing adequate protection. The meter base typically serves as the entry point for electrical service to a building but does not usually contain overcurrent protection devices. The service disconnecting means, located downstream from the meter base, is where the main overcurrent protection is provided. The grounding electrode conductor should be connected at the service disconnecting means to ensure effective grounding of the electrical system. The neutral conductor is the grounded conductor in an electrical system that carries current back to the source. The neutral conductor is typically grounded at the service disconnecting means to establish a reference point for voltage and provide a path for fault current. The National Electrical Code requires that the neutral conductor be insulated and sized appropriately for the intended load. Understanding the functions of the grounding electrode conductor, overcurrent protection, meter base, and neutral conductor is essential for designing and installing safe and effective electrical systems. Adhering to National Electrical Code requirements and best practices ensures the protection of people and property from electrical hazards. Let's explore the implications of grounding the neutral in multiple places. Grounding the neutral conductor in multiple locations, such as at both the meter base and the main overcurrent protection, can create several problems. Firstly, it can lead to circulating currents on the grounding system, which can cause nuisance tripping of overcurrent devices and increase the risk of electrical noise and interference. Secondly, it can compromise the effectiveness of the grounding system by creating multiple paths for fault current, which can reduce the overall impedance of the grounding path. Thirdly, it can violate National Electrical Code requirements, specifically Section 250.24 A5, which mandates that the grounding electrode conductor be connected at the service disconnecting means or the overcurrent device for feeders. Therefore, it is crucial to avoid grounding the neutral conductor in multiple locations and to adhere to National Electrical Code requirements for grounding electrical systems. Let's talk about grounding electrode conductor sizing. The grounding electrode conductor must be sized appropriately according to National Electrical Code Table 250.66 to ensure it can safely carry fault current. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. For example, if the service entrance conductors are 200 amps, the grounding electrode conductor must be at least number 6 copper or number 4 aluminum. It is essential to consult National Electrical Code Table 250.66 to determine the correct size of the grounding electrode conductor for the specific installation. Using an undersized grounding electrode conductor can compromise the effectiveness of the grounding system and increase the risk of electrical hazards. Furthermore, it is essential to ensure that the grounding electrode conductor is properly protected from physical damage and corrosion. The conductor should be installed in a raceway or otherwise protected from mechanical damage. Connections should be made using approved connectors and methods to prevent corrosion. Let's explore common misconceptions about grounding. Firstly, there is a misconception that grounding the electrical system is not necessary. Grounding is essential for electrical safety. A grounding system provides a low impedance path for fault current, facilitating the operation of overcurrent protective devices and minimizing the risk of electrical shock. Secondly, there is a misconception that any metal object buried in the ground can serve as a grounding electrode. A grounding electrode must meet specific requirements outlined in the National Electrical Code, such as being a metal underground water pipe, a concrete encased electrode, a ground ring, or ground rod. Thirdly, there is a misconception that the neutral conductor and the grounding electrode conductor are interchangeable. The neutral conductor and the grounding electrode conductor have different functions and should not be used interchangeably. The neutral conductor carries current back to the source, while the grounding electrode conductor provides a path for fault current to the earth. Therefore, it is crucial to understand the functions of each conductor and to adhere to National Electrical Code requirements for grounding electrical systems. Let's discuss the importance of proper grounding connections. Proper grounding connections are essential for ensuring the effectiveness of the grounding system. Grounding connections must be tight, free of corrosion, and made using approved connectors and methods. Loose or corroded grounding connections can increase the impedance of the grounding path, reducing its ability to safely carry fault current. Approved connectors, such as compression connectors or exothermic wells, should be used to make grounding connections. These connectors provide a secure and reliable connection that is resistant to corrosion. Regular inspection and maintenance of grounding connections are essential for ensuring they remain in good condition. Connections should be inspected for tightness, corrosion, and damage and repaired or replaced as necessary. Let's look at the role of equipment grounding conductors. Equipment grounding conductors provide a path for fault current to return to the source in the event of a fault. The equipment grounding conductor is typically a wire or conduit that is connected to the metal parts of electrical equipment such as appliances, motors, and enclosures. In the event of a fault, the equipment grounding conductor provides a low impedance path for fault current, allowing the overcurrent protective device to quickly interrupt the circuit and prevent electrical shock. The equipment grounding conductor must be sized appropriately according to the National Electrical Code and must be properly connected to the equipment and the grounding system. Let's discuss grounding electrode systems. A grounding electrode system consists of one or more grounding electrodes that are bonded together to form a common grounding point. Common grounding electrodes include metal underground water pipes, concrete encased electrodes, ground rings, and ground rods. The National Electrical Code requires that a grounding electrode system be used whenever possible to provide a more effective grounding path. The grounding electrodes must be bonded together using bonding jumpers that are sized according to the National Electrical Code. The grounding electrode system should be located as close as possible to the service disconnecting means to minimize the length of the grounding electrode conductor. Let's explore surge protection and grounding. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning strikes or other electrical disturbances. SPD work by diverting surge current to ground, preventing it from damaging sensitive electronic equipment. Proper grounding is essential for the effective operation of SPD. The SPD must be properly grounded to provide a low impedance path for surge current to ground. The grounding conductor for the SPD should be as short and straight as possible to minimize impedance. It is recommended to install SPD at the service entrance and the downstream distribution panels to provide comprehensive surge protection. Let's look at grounding in different types of electrical systems. Grounding requirements may vary depending on the type of electrical system. For example, separately derived systems such as generators and transformers have specific grounding requirements outlined in the National Electrical Code. Separately derived systems must be grounded at the source of the system, and the grounding electrode conductor must be sized according to the National Electrical Code. It is essential to consult the National Electrical Code to determine the specific grounding requirements for different types of electrical systems. This ensures that the electrical system is properly grounded and protected from electrical hazards.